All right, make sure you have a calculator today, and we're going to open up to page 453. In this section and the next section, which happens to be the last section, we have two more. I know, the end is near, light at the end of the tunnel. We're going to be talking about volume. And in order for us to understand how to calculate the volume of these really weird looking shapes, 453. Okay. In order for us to understand how to calculate the volume of these really weird shapes, we first have to understand how volume is related to area, because we've been doing a heck of a lot with area the last month or so. Now, just before we make that connection, I need you to understand that if we were finding the volume of a cube, or the volume of a prism, or the volume of a cylinder, that would be really easy for us because we have geometric formulas to help us with those. It's when you have a really weird looking shape, for instance this vase, like kind of on its side, like it gets a little difficult to use those geometric formulas to help us. So this is why we're going to utilize calculus and area to help us with that. I'm going to write down two equations at the top. The first one is going to be the surface area of a sphere. That equation is 4 pi r squared. And the second one I'm going to write down is the volume of a sphere. That's 4/3 pi r cubed. Okay? One of them is an area equation. The other one is a volume equation. These are for a sphere. Okay, geometric shape of a sphere. What is a calculus relationship between those two equations? Can you see it? What do you see, Daniel?
The integral of surface area is the volume.
There you go. If you work backwards from area, aka integrate area, wouldn't you get this? You would add 1 to the power, which would be 3, and then you have to divide by that new power, which would give you 4/3. Do we see that? Okay, so we're going to make note of that connection. We need to integrate area to find volume. We're going to come back to this main idea throughout this section and the next one. So this is a pretty big connection or relationship that we just drew. Okay, so let's think about this. I want you to visualize, which might be a little difficult. Yes, ma'am. Yeah. There you go.
Thank you.
Go ahead. All right. So what we first need to try to visualize, and I know it might be difficult for us, that's why I'm going to show you a computer program or example so the visual is a little bit easier for us to understand. But I want you to take a look at this shape. So notice how we have some type of function. Okay, maybe it's a parabola because it looks like a U, and we're looking at that function from some beginning point to ending point, like from A to B. Do you notice how that shape matches the shape on the right? Can you see the connection between the two? Okay. If you were to take all of this area and revolve it around the x-axis, can you see it in your head how you would generate this shape, that vase? If you were to move it in a circle, can you see how you would create that? It might be a little difficult. That's why I'm going to show you something in a little bit. Okay, but if you were to revolve it, it would look like this. So what we're going to do is we need to figure out the area under this curve, and we're going to rotate it in a circle. And by rotating it in a circle, the area is going to turn into volume because we're going to work backwards from that. Now, in order to do this, since we're rotating around an axis, we are creating a circle or some type of disc, like a frisbee, okay? If we need to integrate area, what's the area of a circle? Remember area of a circle? Yeah?
Pi
pi r squared. Okay, so I want you to take a look at this second equation down here. Do we see the pi r squared kind of setup? Notice how we have the pi, and we're going to integrate r squared. Now the thing is, the r is representing the radius of your circle. This is where we need to kind of analyze the area graph itself. If we were to draw a little rectangle, okay, in that area, and we were to revolve it in a circle, this rectangle is your radius. Because if you make it into a circle, you're going to get the same rectangle down below. Okay, I hope we can visualize that. So notice how the radius is simply your function minus the axis that you are revolving it around. So we have the top, which is the function, minus the axis, which is the bottom. Just like we've been doing the last few days. We have top function minus bottom function. All right. This is what's referred to as, like I said previously, the disk method. Because if you were to draw in even more rectangles, notice how all the rectangles would touch that axis of rotation. So if all the rectangles are touching the axis and you are revolving those rectangles, you're going to create a solid object. Okay, there's nothing missing from the middle of it. It's just one solid three-dimensional object. All right, so I'm going to show you a quick little video that kind of summarizes this method, and as the video plays, I'm going to pay close, or I want you to pay close attention to certain things, and I'm going to highlight certain aspects. So just give me a second to bring that up. All right, so in this example, we're going to start with a simple square root function. And notice how if you were to draw in your vertical rectangles, every single one of them would touch the x-axis. That is the axis that we are going to revolve it around in a circle. So I want you to pay close attention on the visual, okay, what it would look like. Do you see how you can create a three-dimensional object from a two-dimensional area? Okay, we started with a flat area and we revolved it and becomes a 3D object. Notice how this object is completely solid. There aren't any holes or gaps missing in that shape. Okay, I'm going to play it a little bit further. A little slow. There we go. All right, so take a look at this. They're kind of giving you a cross section. They're showing you how the inside of that three-dimensional object is a disk. Okay, that's why it's called a disk method. It's like a frisbee. It's a complete solid circle. Notice how this circle would have a radius from the x-axis, that's where we rotated it around, to the top of the function that we originally had. So the radius is that top function minus the axis we revolved it around. Does that visual help? Can we see that rotation? How you're taking a two-dimensional area and turning it into a three-dimensional object. So far, so good. All right, that's all I wanted from that. Okay, so let's think about something different. What if we were to look at the same example on our paper? Notice how it's the same area, but instead of letting all of the area go down to the x-axis, which is where we were revolving it around, we're only going to let the area go to this horizontal line, y equals c. But we're still going to revolve it around that x-axis. So can you think about visually, if you were to revolve it, it's still going to look like this vase, but what else would this three-dimensional object have? What do you think, Ryan?
It would have a cut out.
It's
Which would be like the diameter. Expanding through the whole length of the object.
this white piece. Yep, the whole length of that white piece. Were you going to add something, Daniel?
I was just gonna say there's a hole in it.
There's a hole in it. Okay, or specifically a cylinder. There's a hole. There's going to be a chunk missing because notice how if we are revolving the area, that's going to be the solid object. But if we're also revolving that white area, you are creating some type of hole. Specifically, it's going to look like a cylinder in this case because we have that rectangle. Okay, so to figure out this area, it's a little bit different because we have two things we have to consider. Let's go ahead and draw in our little rectangles. Notice how if you draw in the rectangles in that area, not all of the rectangles are touching the axis you are revolving around. That means you are revolving white empty space, which is going to turn into a hole or some type of missing chunk in your three-dimensional object. So we're actually revolving two things. We are revolving the area from the curve, but we're also revolving the white space or the white area. So we have to take both of those into consideration. Okay, so take a look at this. We're still integrating area. It's still pi r squared. It's just in a different capacity. So our first radius is the outer function, which would be the curve, because notice how that's the furthest function away from the x-axis that we are revolving around. So we would need our outer function minus the axis, which in this case would be 0. The x-axis is just an equation of 0. And the closer function to that axis we are revolving around is that horizontal line of C, where the bottoms of the rectangles stop. So we would need C minus the axis, which again would be 0. Okay, so we have the outer radius minus that inner radius, and since it's the area of a circle, the radius needs to be squared. They're just both of those powers of 2. Okay, so I'm going to again show you a little video that this is what's called the washer method. If you think about a washer like from a hardware store, it kind of looks like a donut where you have the chunk missing in the middle. Okay, a washer method is where your rectangles don't all touch that axis of rotation because you're going to be creating some empty white space, aka a hole. Right? So I'll show you another little video for that. All right, so we have a basic square root function, and then they're going to throw in this line. And it looks like we want the area to stop at 4. Okay, so there's the area that we're going to revolve. Notice how if you draw in your vertical rectangles, if you draw in your vertical rectangles, not all of them are touching the x-axis that we are going to revolve it around. So this is going to be a washer. We're going to have some empty space to account for. I want you to watch how we revolve it. Can we see how this little like cone shape is that missing piece? Because that was the white that we revolved. Okay. So if you were to think about this, draw this in here. We have the outer radius that we revolved, but then we have the little radius that we revolved as well. So to figure out the volume of the solid, we have to take the outer radius minus that inner radius that is technically white space. Okay, so they'll show you what that looks like in another cross section here. You see how it looks like a donut, aka a washer? Okay, so we have either a disk method, that's if all of the rectangles touch the axis we're revolving around, or we can have a washer method. where some of the rectangles don't touch that axis we're revolving around, which is going to account for some missing area or some missing volume in the end. So what we're going to do is practice both of these methods today and try to identify when is it a disc, when is it a washer. Okay, we're definitely going to need our calculator. All right, let's check out the one on the back. We're going to find the volume of the solid generated by the area of these curves when we revolve it around the x-axis. So I know it might be a little hard to see, but on your paper there is a coordinate system or a graph kind of drawn in there. So this is another vase example. We're going to try to figure out the volume of this vase. And if we were to draw in the curves, x cubed minus x plus 1 would be that upper curve. X equals -1 would be the bottom of your vase. And x equals +1 would be the top of your vase. So we're just going to take the area above that x-axis. Maybe we'll draw in some rectangles. And if we were to revolve those rectangles, they would eventually land on the bottom, creating this vase shape. Okay? So as you draw in those rectangles, do all of them touch the x-axis that we are revolving around? Yes. Okay, this is a disc method. You're going to get a solid circle when you revolve it. Okay, kind of like a frisbee, like I said before. Okay, so disc method. In order for us to figure out the volume, we have to integrate area, which means the area of a circle. We said that was pi r squared. So let's throw in the pi. Can we figure out the bounds of our integral? Where do our rectangles begin? Where do they end? Good, Ryan?
They begin at -1.
Yep.
And they end at +1.
Perfect. Okay. So now we got to figure out what's the radius, aka basically the length of these rectangles you draw in, and we're going to square it. Now, in order to help you figure out that length, we're simply going to take the function that those rectangles touch and subtract the axis that we are revolving around. This is our basic setup for the disc method. We have function minus axis. So let's think about it. All these rectangles are touching that top curve or function, which was x cubed minus x plus 1. And then we'll go ahead and subtract the axis that we are revolving around, which happens to be the x-axis, but what value does the x-axis have? Yeah? 0. Okay, so you don't have to technically write in -0 if you don't want to, but at least we're showing the process. We have the function that the top rectangles touch minus the axis, which happens to be the bottom function. Just like all the area we did yesterday, it was top minus bottom. Same idea here. So on your calculator, I want you to type it in exactly as you see it. The pi button, I believe, is above the caret key on the right-hand side of your calculator. You'd have to hit the blue button first. Alright, so just to recap, we're integrating the area of a circle because we are revolving in a circle, which is pi r squared, and that radius is coming from the length of those rectangles. To help you figure that out, we got to do top function minus bottom function, aka function minus axis. Okay, anybody get it? What's the volume of this vase? I got 6 point something. Does that sound about right? 6.762. Can we get that? All right, half the battle is our setup. Okay, trying to figure out what the equation should look like. I know you guys can type it in. We just got to make sure our setup is correct. All right, let's try the next one. Find the volume of the solid generated when the area bounded by this curve and the x-axis is revolved around the x-axis. Now, there's not exactly a coordinate system on this shape like there was for the last one. So let's go ahead and graph this function to figure out where our coordinates should be drawn. So let's go to y equals, and we'll type in x minus x squared. And I'll just do -2 to +2 for now. We can always change it if we have to. Alright, so they're telling us find the volume of the solid generated when the area bounded by the curve and the x-axis. So that's just this little chunk somewhere up there. So it looks like if we were to draw in a coordinate, that the y-axis should be on the very left-hand side. So that would be somewhere right here. And then this intersection point, or not intersection point, but x-intercept looks like a value of 1. And notice how the top of that shape would be the curve x minus x squared. So the axis doesn't always have to go through the middle of your shape. It could be on the end somewhere to help you out. Okay. Let's go ahead and draw in our rectangles between the curve and the x-axis. Do all of those rectangles touch the x-axis that we are revolving around? Yes. So this is another disk method. You are creating a solid object. There's no white empty space that's missing. All right, so our volume is pi r squared. We're going to integrate that. We can move the pi out front because it's just a coefficient, a multiplier. We can move it out of the integral, but you can certainly put it in there if you wanted to. Can we figure out the bounds? Where do our rectangles begin? Where do they end? What do you think, Ryan? 0 to 1, perfect. All right, so then we got to figure out what is the radius, okay, the length of those different rectangles we draw, and we'll square it. To help us figure out the radius, we need the function minus the axis we are revolving around. Let's see, the function, aka the top of those rectangles, is x minus x squared. And if we subtract the x-axis, that would just be minus 0. All right, from there we have some calculator work. Did you get it, Ryan? Good.
0.105.
5? Okay. I like it. Can we get it? So far, so good? All right, if I'm going too fast, you guys would tell me, right? I hope. All right, let's try the next one. No picture this time, so it might be up to us to actually draw it to get a visual. Find the volume of the solid generated when the area bounded by these lines is revolved around the y-axis. Okay, so it's not the x-axis like the previous two were. Let's keep that in mind. So let's go ahead and graph these. Maybe we can do it in our heads. You can utilize the calculator if you have to. Y equals 6x minus 3 would be a line. We'd start at -3 and up 6 over 1. So it might look something like that. This is just a rough shape. X equals 0 is the y-axis. And y equals 6 is a horizontal line. So the area bounded by those 3 lines we drew would be kind of this triangle shape, I guess. Now we are revolving it around the y-axis. So let's think about this. When we revolved it around the x-axis, we drew in those vertical lines. If we are revolving it around the y-axis, we're going to have to use,
Horizontal.
the horizontal ones. Okay, so let's go ahead and draw in some horizontal lines. Do all of those horizontal lines touch the y-axis? That's what we are revolving around. Yes, okay, so this is another disk method. You are creating a solid shape. If you were to revolve a triangle, you're going to turn it into a cone, like an ice cream cone. Okay, so we're going to try to figure the volume of this cone out. All right, so disk method, volume equals the integration of area. Since we are revolving in a circle, we're going to use the area for a circle, which is pi r squared. Now, we got to be careful, because since we're revolving around the y-axis, we're going to need a dy integral. So the bounds have to come from that y-axis, and we have to make sure we have y's as our equation. So let's think about these horizontal rectangles we drew in. Where do they start on the y-axis, and where do they end on the y-axis? Do you see it, Ryan? Go ahead.
Starting at -3.
Okay, because that was our y-intercept from the line. Good.
And they end at 6.
6. Yep, that horizontal line we drew in. So those would be our bounds on the y-axis. Since it's a disk method, we're going to have to figure out function minus axis. Now the function they gave us was 6x minus 3, but we don't want x's in our function because we are revolving around the y-axis. So how can we change this function to have a y variable in it instead of that 6x minus 3? Yeah?
Solve for x instead.
Let's solve for x. All right, so let's try to get the x all by itself. We can add the 3 and then divide the 6. So we have 1/6 y plus 1/2. So that's our function in terms of a y. And then we have to subtract the axis that we are revolving around. We are revolving around the y-axis, which has a value of what? What do you think, Liam? That's 0 as well. Just like the x-axis has a value of 0, the y-axis has a value of 0. It's like your starting axis, initial axis, starting, or a value of 0. So there's our setup in terms of the y-axis. Let's go ahead and use our calculator to help us find the volume. Any luck? I know it's y's on your paper, but you can use x's on your calculator. Still should get the same value. Any takers? Did you get Daniel? Go ahead.
21.206.
I like it. 206. How's it sound? Pretty good? Perfect. All right. You ready to try some more? Practice, 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 okay? Let's check out the next one. All right, consider the region pictured to the right. Okay, so they're actually giving us a graph in the area, which is fantastic. Less work we have to do. The graphs are y equals x squared and y equals x plus 2. So we have a parabola and the line. Yes? Good luck. Okay, yep. All right, let's check out the first one. Find the volume of the solid formed when the shaded region is rotated around the x-axis. Okay, so maybe we'll draw in that little loop. If you were to draw in your rectangles, do all those rectangles touch the axis we are revolving around? Are we creating a disk? No, this is going to be a washer. Because if we are revolving from -1 to 2, notice how we are revolving some white area as well. That's going to create some missing hole or missing chunk. So we have our washer set up. This is what's a little bit difficult because we have to figure out what's the outer function, what's the inner function, because we have those two different pieces to consider. We have the area or the region we're revolving, but also the white area that we're revolving. All right, so let's check out our setup for a washer. It's going to start off the same way. Okay, pi in an integral. Looks like the area goes from -1 to 2. And we're going to have 2 radii to consider. So let's go ahead and section this off. We are going to subtract the radii because we want to remove the white area that's being revolved. That's creating a missing hole or chunk in our solid. All right, so the first radii we have to consider is the outer function minus the axis. If we are revolving around the x-axis, which function is furthest away from that x-axis? This would represent the outer, okay, the furthest one. Yeah.
The x plus 2.
That'd be the x plus 2. That's the line. Yep. Furthest away from the axis we are revolving around. So we'll have x plus 2. And then we have to subtract the axis that we are revolving around. Yeah. Yes. We are revolving it around the x-axis, which is a value of 0. So that's our outer radius. That would be from the middle of the circle to the very end of the circle. We do need to subtract the white area now, which is going to have a different radius. So this would be the inner function minus the axis we are revolving around. So in relation to the x-axis, that's what we're revolving around, the inner or closer function, notice, is the parabola. So we would have x squared. Minus the axis we're revolving around, that again, that's the x-axis, so that would be a value of 0. So it's basically the disk method twice. We have to do it twice because we have an outer function and an inner function to consider. Okay, so from there it's just going to be some calculator work. Type it in exactly as you see it. Anybody get it? Good, Daniel?
45.239.
45 point what?
239.
239, I like it. Can we get it, is the question. Yeah? Alright. We'll stop there for today because the bell's going to ring in a little bit. But tomorrow, we're going to step it up a bit. Because notice how the next few examples, we're going to revolve it around something other than the x-axis. So we're going to see how that kind of changes our setup and then therefore the volume. Okay?